Euler's Totient theorem is a generalization of Fermat's little theorem. While the latter specifically applies to prime numbers, the former is applicable to all positive integers. It states that n divides a raised to the totient function of n minus 1 when n and a are coprimes. The totient of a positive integer n is the number of positive integers less than n that are relatively prime to n. When n is a prime p, then there are p minus 1 values that are relatively prime to p. Thus, the totient function of p equals p minus 1. And so, p divides a raised to p minus 1 minus 1, which actually is Fermat's little theorem. So, Fermat's little theorem is just a special case of Euler Totient theorem. When n is composite, we need to consider all its prime factors, thus dealing with the alpha sub I powers over prime factors p sub I. That is, we need to compute each totient of p sub I raised to alpha sub I. Considering p raised to alpha, between 1 and p raised to alpha, there are a number of multiples of p. We got p, 2 times p, 3 times p, 4 times p, etc. until we reach p squared. And then we got 2 times p squared, 3 times p squared, etc. until we reach p cubed. And we can do also the same until we reach p raised to alpha. Upon summation, the number of multiples of p are p raised to alpha minus 1. So the totient of p raised to alpha is the difference p raised to alpha minus p raised to alpha minus 1, which is equal to p raised to alpha minus 1 times p minus 1. So, following those few steps, we find that the totient function of n equals n times 1 minus 1 over p sub 1 times 1 minus 1 over p sub 2 times etc. Let's consider an example. For 1323, which is equal to 3 cubed times 7 squared, its totient function is the totient function of 3 cubed times the totient function of 7 squared. Considering 3 cubed, the multiples of 3 up to that number are 3, 6, 9, 12, 15, 18, 21, 24, and 27. Upon summation, the number of multiples of 3 are 9, which is equal to 3 raised to 3 minus 1. So the positive integers less than 3 cubed that are relatively prime to 3 are 3 cubed minus 3 squared, which is equal to 3 squared times 3 minus 1. Next, we compute the same for 7 squared, whose multiples up to that number are 7, 14, 21, 28, 35, 42, and 49. So there are 7 multiples in that range. Thus, the relatively primes to 7 are 7 squared minus 7, which is equal to 7 times 7 minus 1. Finally, we can compute the totient of 1323, which is equal to 1323 times 1 minus 1/3 times 1 minus 1/7, which is equal to 756. This yields that 1323 divides a raised to 756 minus 1 when n and a are relatively primes. We already showed why the totient of p raised to k equals p raised to k minus 1 times p minus 1 by summing the multiples of p up to p raised to k. That is the keystone of the Euler's totient function for composite numbers, as the function is multiplicative for the prime factors. Therefore, establishing the validity of the totient of p raised to k equals p raised to k minus 1 times p minus 1 stands as a crucial milestone in proving Euler's totient theorem. Below, we offer a proof of the totient function of p raised to k equals p raised to k minus 1 times p minus 1 by the method of infinite descent, which eventually shows that Euler's totient function is supported by Fermat's little theorem. That is, we show that a raised to p minus 1 times p raised to k minus 1 minus 1 is divisible by p raised to k when a and p are relatively primes. To initiate, Let's expand the binomial equation and arrange the first and last terms on the left side of the equation. Next, on the right side of the equation, we can regroup terms with same binomial values. Here we have a raised to p minus 1 raised to p raised to k minus 1. As Fermat's little theorem states that p divides a raised to p minus 1, so here we have that p raised to k minus 1 divides this first term on the left side of the equation. Then, if p raised to k divides this sum on the right side of the equal sign, then as p raised to k minus 1 is much bigger than p raised to k, then p raised to k should divide a raised to p minus 1 times p raised to k minus 1 minus 1, which is actually what we want to prove. As we need to prove that p raised to k divides this sum, we have to deal with two cases. The first case is when there is no common factor between p raised to k minus 1 and I. And the second case is when there is a power of p that is their greatest common factor. When the common factor is 1, then p raised to k minus 1 divides the binomial p raised to k minus 1, choose I. Plus, p divides the difference of the terms in the summation formula, as adding and subtracting 1 for each term yields in a Fermat's little theorem situation. So p raised to k divides the terms of the summation when 1 is the greatest common factor of p raised to k minus 1 and I. When instead p raised to omega is the greatest common factor, then I equals m times p raised to k minus 1 minus u, where u is bigger or is equal to 1 and smaller than k minus 1. And it can be proved that p raised to u is the largest power of p that divides binomial p raised to k minus 1, choose m times p raised to k minus 1 minus u. This particular point deserves special care and will be explained in the third section of this presentation. Next, we follow a few steps. First, replacing I, then regrouping, and finally adding and subtracting 1 to each term. If p raised to k minus u divides a sub 1 raised to p minus u times p raised to k minus 1 minus u minus 1, then p raised to k divides the product of the binomial and the difference of powers. Thus, it divides each term of the summation. Consequently, we prove divisibility by p raised to k only when a sub 1 raised to p minus 1 times p raised to k minus 1 minus u minus 1 is divisible by p raised to k minus u. Should we try to prove this later condition, then certain terms of a binomial expansion, where the greatest common factor of p raised to k minus u minus 1 and I is bigger than 1, would require that a sub 2 raised to p minus 1 times p raised to k minus 1 minus u minus v minus 1 be divisible by p raised to k minus u minus v, and so leading to an infinite descent. This descent holds when the sum of the exponents k minus 1 minus u minus v, etc. equals 0, and therefore p raised to k minus u minus v, etc. equals p, which divides a sub n raised to p minus 1 times p raised to 0 minus 1, which is equal to a sub n raised to p minus 1 minus 1, which we already know it's true, as that's the divisibility certainty provided by Fermat's little theorem. Thus, Euler's Totient function for p raised to k is ultimately proven by Fermat's little theorem. And as Euler's Totient theorem is multiplicative for their prime factors, that's all we need to prove it by infinite descent. Well, that explanation might have been a bit too wordy. An example will make it easier to understand. Let's assume p equals 5 and k equals 3. So, in the first step, as 5 raised to 5 squared divides the first term on the left side of the equation, Then we need to prove that 5 cubed divides every term of the sum at the right side of the equation in order to prove that 5 cubed divides a raised to 4 times 5 squared minus 1. Below, we see every term of the summation, and then a table with each binomial value, where 5 squared divides each binomial value with exception of binomial 5 squared, choose 5, and binomial 5 squared, choose 10. As we already know that Fermat theorem applies in the difference of powers, thus 5 divides a biquadratic minus 1, then what we need to prove for those two special cases is that 5 squared divides a raised to 4 times 5 minus 1, in order to prove that 5 cubed divides a raised to 4 times 5 squared minus 1. And that implies going through a descent. So the next step is proving that 5 squared divides every term of this sum, in order to prove that 5 squared divides a raised to 4 times 5 minus 1. And as inside of the summation we have that each bracket is a Fermat theorem case, so 5 divides each one. And as 5 also divides the binomial values, then 5 squared divides each term of the summation. Since every term of this sum is divisible by 5 squared, it follows that 5 squared divides a raised to 4 times 5 minus 1. By establishing this through an infinite descent, we are certain that 5 cubed divides a raised to 4 times 5 squared minus 1, thereby resolving the initial problem presented. In this second section, we describe how Euler's Totient theorem is a generalization of Fermat's little theorem, as the divisibility condition applies not only to prime numbers, but all positive integers. And we were successful in proving Euler's Totient theorem through an infinite descent method, just as we did with Fermat's little theorem in the first section. In fact, the infinite descent emerges when dealing with binomial coefficients. Binomial p raised to alpha, choose m times p raised to beta, where the greatest common divisor of p raised to alpha and m times p raised to beta is a power of p, and eventually culminating when reaching a difference a raised to p minus 1 divisible by prime p, which we already know is true as that's established divisibility condition for Fermat's little theorem. However, one assumption remains to be proven. We presuppose that u is the biggest power of p that divides the binomial coefficient p raised to k minus 1, choose m times p raised to k minus 1 minus u. The following section aims to validate this assumption, or at least offer compelling evidence. We'll use Legendre's formula for that matter, plus derive a clearer, more intuitive alternative.